Great. Let's get started. First of all, any questions in general? Okay, great. Okay, let's briefly review what we covered in our last lecture. So basically, in our last lecture, we formally introduced the concept of modulation, right? And here is the most general definition of modulation. So modulation is nothing but we map information to a signal that is appropriate to be transmitted over a channel, right? So that's the most general concept of modulation. And then we introduce the definition of carrier and the carrier frequency, right? So basically, a carrier is a sinusoid signal that can be used to move the power spectral density of a message signal to a different frequency band, right? So basically, by using the carrier, we can move the signal to a different frequency band, right, for transmission. And the frequency of this sinusoid is called the carrier frequency, and usually it is denoted by FC, C means carrier, or F naught. Okay, so that's the convention. All right, and so this is the simplest form of modulation. So basically, you can see that. So we have seen this many times, right? So M of T basically that is denoted as the message signal, and then the carrier is cosine 2 pi FCT, right? If we do this operation, so basically in the frequency domain, so we move the signal to the right and move the signal to the left and add them together, right? So I have scaling factor here. We don't want to forget about, right? And clearly from this example, we can see that by doing this modulation operation, so we move the signal in the frequency domain, right? So that's very, very good. And next, we introduce the general form of modulation. So basically, we can just generalize the previous formula, right? So basically here, so we have an amplitude here, and then we add a frequency change, and here we add a phase change, right? And actually, all of these three parts can carry information, right? Because they can be changed, right? And we have three kinds of modulation. The first one, if A of t varies with the change of the information, so basically we call that amplitude modulation. And if the frequency varies with the message, then we call that frequency modulation. And if the phase varies with the information, then we call that the phase modulation. Right? We have three forms of modulation. We're going to go over each of them one by one in this class. And we'll start with the simplest form, which is the amplitude modulation. Right? And so this is what we mean by amplitude modulation. And we come back to our most familiar signal. And here we introduce the concept of modulator. So basically, usually, narrowly speaking, modulator is a circuit for generating the modulated signal, right? The circuit generates S of t. We call that as a modulator, right? But normally, this behavior, we just call this behavior together as a modulator. And in particular, so this modification operation, so that's called as a mixer, right? So in industry, you always hear this kind of word, okay? So precisely speaking, so mixer basically means we have two signals multiplied together, right? That's kind of mixing them together, and usually one of them is a carrier frequency, okay? And then we see one example, right? If you remember, so example is like the square. Kind of we transmit a bunch of square waveform, right? And we modulate the square, or we multiply the square with a -1 + 1, right? And for this kind of signal, and in particular, that's called BASK or BPSK, okay? And the reason for the same thing we have two signal is that for BPSK, that's a phase shift key, right? So this is a phase modulator. So basically, we use like 0 means 1, and if we shift the phase by pi, that means a -1, right? If we add a pi there equivalently because it's cosine, or yeah, because it's a cosine, then equivalently we multiply -1 in front, right? That's why BPSK and the BSK are the same. Okay, so yeah, if you don't recall, just look at the notes. Okay, and finally, we introduced the concept of double sideband surprised carrier, so or DSBSC. So basically, that means this kind of modulation, right? So clearly, so why the reason we call that double sideband is because we move the signal. Yeah, it's because for the signal we have the lower sideband and the upper baseband, right? So if you don't recall, so basically what we got is like this. Right, so that's after the modulation, and it's kind of symmetric, and we have both this part and this part, right? That's why it's called double sideband. Okay, we have we have this and that, right? And the other thing, the reason we call it surprised carrier is that we don't transmit the carrier in this signal, right? So what we mean is that we don't transmit a cosine 2πfc, right? If we add another 2πfc here, cosine 2πfc here, so then we don't have this SC anymore. Okay, so we're going to see an example of that today. Okay, so this is what we covered in the previous lecture. So any questions? Okay, so for today, so we're going to talk about demodulation. Okay, so basically the meaning of demodulation is to get the original signal back from the modulated signal. Okay. Okay, so basically the goal of demodulation is to get MF or MT right from SF or ST. Okay, you remember, so now we focus on the case where ST just equals to MT times cosine 2πfct, right? Yeah, does that make sense? Okay, so in practice, normally, this S basically means kind of, sent information, right? So yeah, because now we don't consider any channel yet, right? So in practice, we also use RT that represent the received signal, right? So RT can be equal to that, right? But here we just use S of t because we don't have any noise or channel information, channel state information. Okay, so let's see, this is our received signal. Okay, and then how can we recover M of t from this? Oh, by the way, did you see this kind of thing from your signal system class? Probably yes, right? So normally we use that as a simple example of an application of signal system.
What was the question?
Yeah, the question is, how can I recover MT from ST? Yeah, how can we get MT from ST or get MF from S of F? Yes?
Can't you just divide by the cosine?
You cannot. Yeah, normally, yeah, the operation is to kind of pass this guy through some kind of linear system, or we call that linear filter to get the result, normally. Or something nonlinear, but it's very simple to implement. Right? For example, we can do some multiplication, multiply this guy by another signal, and then do some low pass, high pass, band pass filtering to get M of t. Yeah, we cannot divide this. But it's a very good guess. Yes?
In the lab, we mixed it with another carrier.
Yes.
You do that and then filter.
Exactly, very good. Yeah, clearly you did the lab, right? So yeah, and I know who didn't do the lab. So Okay, so basically what we do is it's a very simple process. So let's see whether that makes sense or not, right? So we do nothing but multiply this cosine 2 pi of ct again on the signal. Okay, so that's what we do. Let's see whether that works or not, right? So basically we do nothing but we mix it. Remember, mix basically means multiplying, right? So we mix that guy with the carrier again, okay, at the receiver. So normally we use Rx to represent the receiver and Tx to represent transmitter. Okay, so let's see what we got, right? So basically if we do that, and then, so what we can get is as follows. We have mt cosine 2 pi fct squared, right? Because we multiply the carrier again, right? So this is what we got at the transmitter, at the receiver, okay? And yeah, let's see what does that equal to. Okay, so we have a cosine here. So can we do some, trig identity to simplify it? Remember, cosine squared equals to whatever something add some cosine, right? So let me remind you. So basically, what we can do is as follows. So this guy equals to half 1 plus cosine 4 pi fct. Right, we have a 1 here, and we just double the angle. And then we have a half here. Okay? Yeah, let's maybe write it in a nicer way. So mt over 2, 1 plus cosine 4 pi fct. Right? So that's in the time domain. Let's see what is the signal in the frequency domain, right? If we denote it as E of t, and then what is E of f? Yeah, can you tell me directly what the signal is in the frequency domain? Yeah, the symbol part is the first part, right? So mt over 2 times 1 is just mt over 2, right? So that's half mf, right? So that's it. And so what is the Fourier transform of mt over 2 times cosine 4 pi fct?
1 over 4.
Very good. And
Cosine, or sorry, m of f minus 2. Yeah, and then plus 2.
very good. Right, so it's exactly the same operation, the operation as this, but now we double the frequency here, right? So that is what we got. That makes sense? Okay, so now let's see what does that look like, right? So here we have 3 frequency components. Okay, so in the middle we have our m of f, right? And let's see here, it's half, right? Let's assume, whatever before the magnitude is 1. Okay, so this is our mf over 2, and then we have 2 additional signals, so that has a lower amplitude. Okay, but here the frequency is high, it's 2fc, and here is minus 2fc, right? So this guy is mf minus 2fc over 2, and this guy is mf plus 2fc over 2. Okay, so this is what we got for the EF. Okay, great. Yeah, clearly in the frequency domain, maybe that is a little bit easier to watch, right? So this is what is exactly going on, right? And from here, can you recover the original signal m of f?
Just low pass filter?
Yeah, exactly. Just a low-pass filter, right? So what we do is nothing but just get this part out, and then those part will be gone, right? So it's a low-pass filter, LPF. Yeah, I need to bring some colored marker. Don't have anything here. Okay, so basically in summary, so what we have is as follows. So we have our S of t, right? And then we do a modulation. So we times that using cosine 2 pi of ct, right? Or sorry, it's a mixer, right? This is not a modulation, so because that is receiver, okay? And then we got our e of t, right? And then after that, we pass our signal through LPF. Yeah, here we can scale the magnitude by a factor of 2 because we have a hub here, right? So LPF and then scale by a factor of 2, and then we can get our m of t back, right? So this is what we get, and that's it, right? That's the receiver. Is that okay? Any questions? Yeah, relatively straightforward, right? So now let's give some definition here. So normally for this part, so we call that our baseband signal. Yeah, and for those parts, so that's for higher frequency signal. Okay. Okay, very good. Okay, so that's a demodulation. Are we done? So in other words, so for this simple operation, do we have any problems of it? Right, seems a very straightforward and simple process, right? So do we need to develop anything else for the demodulation, right? Let's say, so this is what we transmit, right? We just consider this kind of form for transmission. And is that perfect? Right? In order to see whether it is good enough or not, right, we just need to see what kind of operations do we have here, right? So one operation, so which is a mixer, and the other operation is LPF. So is there any problem for these two operations? Yes?
Maybe that signal that you received is not, perfectly like multiplied by that cosine 2 pi f naught t. Like maybe there's some added stuff it got in it from transmission.
Almost there. Yeah, it's a very good thinking. So yeah, we think along this line. Yeah, for this guy, yeah, we don't consider noise so far, right? Let's say this is perfectly received. Okay, but we need to think along this kind of line. Okay, so remember, so we call that what? DSB SC, right? So why we need to emphasize on this SC part? Yes?
Is it maybe because in your received signal you don't know what FC is?
Almost there. So FC is easy to know, right? Just tell the receiver, right? For example, FC is just a single point in the frequency, right? If it's 2 gigahertz, and then I just tell the receiver using the 2 gigahertz, but it's almost there. So FC, no problem. We know FC. But the problem is that, yeah, we're almost there. So LPF normally don't have any problem here, right? But the problem is normally here, right? So this guy is now transmitted. We know FC, but how can we be sure that we can perfectly generate this guy? Make this guy exactly equal to this guy, right? What are the missing part?
The phase.
Exactly, or the delay, right? So we need to perfectly align this and that. That is very hard. Okay, let's see an example. Let's see what I mean exactly here. So normally, let's say we can generate cosine 2 pi of ct, right? For some time reference. But for the transmitted signal, so what we received exactly may not be this guy, right? Because it takes time, for a signal to transmit, right? And the time is called delay, right? So in practice, so basically what we receive is as t minus tau instead of t exactly, because the time slot when the time stamp when we transmit is t, but when we receive it, it takes some time, right? It's very fast, speed of light, but still takes some time, right? Okay, and this tau is called propagation delay. Okay, so if we write it exactly, it will be like this, right? So we have delay here, and then we have delay on this cosine, right? And why it matters, right? Because normally the speed of light is super fast, right? Why this tiny time matters? So in order to see that, we need to, break it. Okay. Yes.
Is it because of how high the frequency is?
Exactly. Very good, right? So the speed is very fast, but normally, so this frequency is, so tau is very short, but frequency can be very high, right? If frequency is 2 gigahertz, it's 2 times 10 to the power of 9. Right? It's comparable to speed of light, right? So frequency can be very high, right? Therefore, in practice, so this guy really matters. It can be any value, okay? Okay, so now let's see one explicit example to see why it matters. So if we denote this as theta, right, because it's a phase, right, just denote that as theta. So let's say if theta equals to pi over 2, let's see what will happen. Right, as we said, theta can be anything from 0 to 2 pi, okay, because FC can be very large, right? So if FC is extremely small, then I don't think it matters. But in practice, FC is always like in the order of gigahertz. Right? Okay, great. And let's assume theta is pi over 2. Let's see what will happen in this case. So now S of t will equals to what? Let's say if this guy is pi over 2, then the cosine something minus pi over 2 becomes what? Yeah, sine, right? Right, cosine, we shift it to the right by pi half, right? So that's sine. Then it basically means that we have mt minus tau times sine 2 pi fct, right? So this is what we got. Okay, and now let's use the same thing. Let's use the same structure to do the demodulation, right? We multiply this guy with cosine 2 pi fct, right? Because I don't know the shifting, right? I just use cosine here for the demodulator, right? So E of t equals to mt minus tau sine 2 pi fct cosine 2 pi fct, right? Use this, multiply that. So now, can you tell me what that equals to? Sine times cosine? Yeah, that should be easy, right? Sine theta times cosine theta equals to, yeah.
1/2 sine 2 theta?
Very good, right? So that's a formula. Yeah, I think that is relatively easy. You should remember it. 2 times 2 pi, so that's 4 pi. 4 pi fct, right? And then we multiply that by this guy. Okay, so this is what we got, right? So compared to before, so before, this is what we got. Okay, so I have cosine square here, and then we have this. But now we have that. What's the difference? In other words, can we still, using this approach, passing that through LPF to get our original signal back? We cannot, right? Because now here we don't have the constant part here, right? So this guy is only for the high frequency, right? The high frequency component at 2FC, right? So we only have the high frequency component, and we cannot get things back. Okay, and we're doomed, right? So the cause of it is just this frequency shift. That makes sense? Okay, so I have another example in my lecture notes, and you can take a look. So the idea basically is the same, right? Let's say if we have theta equals to pi, then you can do the same manipulation and see what will happen, right? So basically, if theta is pi, then if it's minus pi, then we'll have minus sign in front, right? So this will also not work for some kind of signal, okay? Like BPSK, ASK. Okay, great. So yeah, we skip that, and you can look at that after offline. Okay, great. So now let's see how we can solve the problem, right? So we have this problem. We have this phase shift problem, right? So any idea how to solve it? right? Any idea? Yes.
Could you, like, if you transmitted a carrier?
Very good. Exactly. As we said, right? The problem is that we didn't transmit the carrier, right? If we transmit the carrier along, so they're going to have the same delay, and then the problem is solved, right? Yeah, very easy, right? So that's the first way to solve it. So we have two ways to solve it. Okay, the first way, yeah, is it's very intuitive. So we just send a carrier along with the signal with the DSB SC signal. Okay, and now we don't have this SC anymore, right? In this case, okay, but we have another name for it. Can I take a guess? DSB? No. Oh, how do you know that? yeah, you're in the amateur radio club, right? So you should know that. So actually, it's kind of funny. It's called AM, right? That sounds familiar. AM means amplitude modulation, but it only means this kind of amplitude modulation. It's a very specific word, right? We can now call any amplitude modulation as AM, right? When we say AM, it means that we transmit the DSB signal, DSB SC signal, but with a carrier. For this kind of thing, we can use the abbreviation, right? We can now use them arbitrarily, right? This is called AM. Very good. And can you think another way to do that? So that'll be our focus, okay? But there's another way to do that. Yeah, for this way, it's like, okay, so now we just transmit the carrier along with the signal, right? And then, that makes sense, right? But another way that we can do it is, so we transmit m of t times cosine 2 pi of ct, right? I mean, all information are there. So is that possible that we can locally generate something to estimate the phase? Right? If we know the phase, then we're fine. Right? Does that make sense? So basically, that is another way to do that. So yeah, I'll write it down. So basically, who heard of PLL? Yeah, so that's the way we do that. We use a phase lock loop to do that, right? So basically, that is to use. Yeah, we're not going to touch it in this class because designing a PLL is an entire class normally. Okay, use a control loop to match the phase of the local carrier to the phase of received signal. So yeah, that is called the phase log loop. So basically, we estimate the phase and then we log it, right? Or LLP. We're going to focus on the first method, basically. Okay, but there are two methods to solve the problem. Okay. Okay, very good. So now we're going to take a look at the AM signal. Yes.
Does it matter if the LPF is like a linear phase filter, or is that not what we're talking about here?
It's a linear, yeah. All the filter we talk about is linear phase.
Like if it's not like a linear phase filter, though, like can you still do this?
You mean if that's not linear phase?
Yeah.
Don't understand your question. So why we want to use that?
I'm just asking if it were like I don't know. I had a class where we made like Butterworth and like Chebyshev filters, and like they aren't linear phase.
Yes.
So like you couldn't use that for this application.
Yes, that's exactly what we use in our lab, probably. Yeah.
Oh, so you still can use it.
Yeah.
Okay. Cool.
That's linear phase, right? It's not linear phase.
I didn't think they weren't like.
The Butterworth and Chebyshev is not linear phase.
think the only ones we had that were linear phase were the FIR ones that we made.
Yeah, let's maybe we can double check it. Yeah, if it's not a linear phase, but based on my understanding, so it can be sort of approximated as a linear phase.
Okay.
Yeah, if the phase is not linear, then yeah, we're gonna have some trouble.
Yeah, because that messed up my last lab in the class.
Yeah, I'll double check it. Okay, very good. Okay, so for AM signal, yeah, as we said, right, so basically what we do is only to add a carrier on the signal, right? So let's see what does SAM look like, right? So that's basically add a carrier. We use A multiply 2 pi FCT. Yeah, I think the phase has to be linear. If the phase is not linear, because if the phase is linear, then the time domain is a shift, right? I think that's fine. But if the phase is not linear, then who knows what will happen in the time domain? It has to be specific, right? I guess in some domain it can be approximated as a linear phase, I guess. Yeah.
Well, like the Butterworth is linear magnitude.
Yeah.
Chebyshev is linear phase. So use a Chebyshev for like if you want to keep the phase linear.
Yeah, probably. Yeah, it has to be. I think it has to be linear phase. If the phase is not linear, then what should they do? Yeah, everything we talk about in communication is linear. Yeah, even though sometimes the channel is not linear. Sometimes the channel is. Yeah, the channel is always linear. So we can deal with a case where it is time varying. Yeah, but it has to be linear. If it's not linear, then there are lots of trouble. Like for example, the power amplifier, so it has some nonlinear effect, right? Then we'll deal with it, case by case. Yeah. The same for the phase, right? If the phase is linear, then I think it's good. In the time domain, it's just a delay, right? If it's not linear, then yeah, we'll have to deal with it. Okay, great. But sometimes, we can do something nonlinear, including, we're going to talk about, probably not in this class, probably next one. So sometimes we do nonlinear operation because that can be easier for some circuits. Yeah. Okay, anyway, so let's go back to our AM signal. So basically, this is our modulation, right? So for this part, it's exact same as before, DSBSC. Okay. And this part is our carrier, right? So just a pure carrier. Right, we need a magnitude here, right? Depends on the implementation. Okay. All right, so then we can write that as m of t plus a times cosine 2 pi FCT, right? Okay, and so this is basically the AM signal in the time domain, right? Let's see what is that in the frequency domain. Okay, so basically that is also relatively straightforward, right? The only difference here is that we need to add the frequency, the Fourier transform of this guy, right? Which is 2 delta signal. Okay, so I'll write it directly. So basically, for the first DSBSC part, we have half m minus fc and m f plus fc, right? And for the carrier part, we have a over 2 times delta f minus fc plus delta f plus fc, right? And in the frequency domain, so basically it looks like this. So we'll have the same thing as before. Right, the only difference here is that we have a delta signal here at minus fc and at fc. Right, so that's basically the signal in the frequency domain. Any questions? Yeah, that is straightforward, right? Now let's see an example. How we can do the demodulation given this kind of signal, right? Actually, we can do something much simpler. Okay, and let's see why this can solve the problem as we raised before, right? So let's assume a signal look like this. Right, this is the most typical shape of a signal we talk about when we talk about AM modulation. Right, so let's see, this is our MT. Okay, so if this is our MT, and so basically what we do is that we add an A on top of it, right? So the non-trivial part is that, so we have something below 0, right? So that's our 0 line. We have something below 0, okay? So because of this, so we have two cases to consider here, right? So one case is that by adding this A, so the total envelope is bigger than 0. Okay, so that's the first case. And the second case is that when this guy is less than 0. Okay, so let's see what happened in each case, right? So for the first one, so when this at A is bigger than 0, meaning that after adding A, we move this part completely above 0, right? So basically, if it's 0 line, so then this is the case, right? Because A is bigger than 0, okay? Then if we use this guy, multiply by cosine 2 pi of C, what do we get? What do we have? Right, imagine it. So if we use this guy by multiply 2 pi of C, so basically for this cosine, we have both negative and positive, right? So eventually we're going to have something like this. And then we have the cosine shape in between. Right, so this is our received signal. This is our modulated signal, right? This is our SAMT. Okay. On the other hand, right? So if we have this case, so basically, so something is still below 0, right? And then after multiplying cosine 2 pi of C, so basically what we're going to have is something like this, right? So we have another version of it, but now, so it has to cross 0, okay? And then this is something in the middle, right? I have these two cases to consider. So which one do you like? First one, why? It looks nicer, right? But why the first one is better? Yeah, the reason is that we kind of have the signal here already, right? So that is the envelope of the signal, okay? Let's say if we have a very smart circuit that can, recover this envelope, then we're good. Okay, in some other way, not the original way, right? Not multiplying another cosine. And let's say we have an envelope detector, then we have recover the envelope directly, right? But here we have the problem, right? So if we have the envelope detector, so our envelope is this guy now. So this here and here, right? But this part is not the envelope, right? It's a negation of the envelope, right? Because we have this cross, so that's a problem, right? So this one is not good, okay? So this one is good, right? That's basically the intuition here. Okay, so from this, okay, so now we just assume that we have an envelope detector, so we can recover the envelope, right? So we're going to talk about that exactly later, right? So hopefully now everybody agrees that. So basically what we need is this guy, right? So A plus MT bigger than 0, to recover the envelope. So this basically means that A has to be bigger than minus MT. Right, so normally we put an equal sign here. Right, if exactly equal, we'll think that is okay. Okay, so we need to make sure this is the case for all t, right? Okay, so in practice, we need so in order to measure the performance of AM, so we need to introduce some concept here, right? So let's introduce it. So in practice, we normally assume that this message signal is bounded, right? So by bounded, basically we mean that so the magnitude is within the range of MP, right? Bigger than or equal to minus MP, and less than or equal to MP, right? So, and since we have this, so basically it means that A has to be bigger than or equal to minus this guy, right? Because that's the smallest value, right? So A has to be bigger than or equal to minus MP, meaning A is equal to, of course, MP is bigger than 0, right? We assume. Okay, so A has to be bigger than or equal to MP, right? Okay, and given this, given this concept, then we have the definition. So that's called modulation index. Right, so basically this can help us to measure the performance of the system, how efficient that is, right? So modulation index meaning this. So basically, that means we use a mu to denote it. So we use MP over A to denote the modulation index. Okay, and here for our envelope detection. Okay, and we consider the case in this case, so mu has to be between 0 and 1, right? Because A has to be bigger than MP, right? So this guy has to be less than 1, less than or equal to 1, and bigger than or equal to 0. Okay, so in this case, we have two cases to consider, right? So when mu equals to 1 or less than 1, right? Less than 1, we can figure out it accordingly. But when mu is equal to 1, so basically meaning that MP equals to A, right? So in this case, so that's the kind of the extreme case, right? If mu is bigger than 1, then it's not okay, right? So when mu is equal to 1, so we say the signal is 100% modulated. Okay, but if mu is bigger than 1, not less than 1, bigger than 1, we say the signal is overmodulated. Okay, given this, so let's introduce the concept of power efficiency. Okay, we can see, so for AM signal, right? So basically what we did is that we transmit another carrier signal, so that is not useful, right? Not useful, I mean, of course it's useful, right? But the reason we say it's not useful is that it doesn't carry any information, right? So only empty part carry information. So this A times cosine, this carrier, so basically it's kind of waste of energy, right? Ideally, we don't want to send it, right? But the reason we send it is for demodulation, okay? Therefore, from this, we can see there's a modulation efficiency, right? We want this capital A to be 0, right? If we don't transmit that, everything transmitted is our message signal, right? But now, so we need to transmit another signal, so we introduce the concept of the power efficiency. Okay, so let's see this definition. right? So basically, the power efficiency means the following. So it's denoted as eta. So normally, if we use eta, it means some form of efficiency, right? So in the upstairs is the useful signal, right? By useful, I mean the message, right? It's the power of the message signal and divided by the total power. Okay, power of the message signal divided by total power, and then we multiply this by 100%. So it's percentage. Okay, so now let's see how we can compute it in practice, right? So actually, it may not be very straightforward for AM signal. Okay, so yeah, now let's do some assumption here. So we assume that our message signal m of t, so we don't have the DC component. So basically meaning that the integral of it give us 0, right? Why is that? So if that is true, then it basically means that there's no DC component. Do you remember? So when we compute the Fourier series, right? So for when f is 0, basically that means a constant, right? So then we use this formula to compute that, right? That's the DC component, okay? Yeah, so that is the DC component. So normally that is denoted as m bar of t, and we assume that is 0 for our computation, right? Yeah, otherwise there will be some waste for transmitting mt, right? So we just do not waste any more additional energy here. And then, so yeah, we won't have 2 minutes. Yeah, I'll just introduce some basic concept here to compute it. So basically, yeah, we use this kind of notation, this norm square notation. Hopefully still remember it. So it's an inner product between a signal with itself, right? But here we kind of abusively use it. We slightly abuse this notation, right? And we use that to denote power, right? So basically, the only difference is that, after doing the inner product, we need to do the integral and divide it by the length of the integral, and then let this length go to infinity, right? But all the property of the norm will stay the same, right? That's why we use that to denote it. Otherwise, it's too complicated to write. Okay, so in this way, we can write the power of the signal as am of t. So that equals to nothing but this guy, right? Cosine. Yeah, just use omega instead of 2 pi f to make it shorter. Okay, and then mt cosine 2 pi, yeah, w omega c t norm. Okay, and how can we, so this is the power, right? And how can we compute it? Kind of complicated, right? So now we have, this plus that together norm, right? So when we want to compute it, we want to break it into different parts, right? Let's see whether that makes sense or not. So we can break it into 3 parts. So the first part is the first item. Yeah, the power of the carrier, and also we have the power of our transmitted signal, our message signal. Yeah. Right? And then we need to add the cross term, right? The cross term is the inner product between this and that, right? So basically, it's 2 times the inner product between a cosine plus mt, not plus, and cosine omega ct, right? Inner product. Okay, so basically, in order to compute eta, so we need to compute this, and that separately, altogether. Okay, and this can be kind of complicated. So yeah, we're going to compute that in the next class. So by the way, can you tell me the first one? Yeah, first one is kind of easy to compute. So what's the power of a times cosine? right, is this. So because cosine is what? Periodic signal, right? So we just integral the square of this guy over one period and normalize it by the length of the period, right? Just use definition, compute it. I think you can do it. So it's just a squared over 2, right? So the first part is easy, right? So this part and this part can be complicated. Okay, so we're going to do that in our next lecture. Great, see you. So happy Valentine's Day.